New York City is one of the most sustainable in the country, due in part to our steam system. Our project explores Con Edison's steam system, how efficient it is, and how cogeneration, a method of generating both steam and electricity, could be utilized to make the system more sustainable.
Too much carbon monoxide for me to bear.
Con Edison's steam system is a network of pipes and boilers that produces and transports steams. Steam systems are most efficient where population is densest. In New York City, population is concentrated in Midtown and Lower Manhattan. That is why the steam system stretches from the Battery to 89th Street on the east side and 96th Street on the west side.
New York City's steam system is supplied by 7 steam plants, all of which are owned by Con Edison except for the Brooklyn Navy Yard cogeneration partners. Along with the BNYCB, the East River Station are cogeneration stations, meaning that they produce both steam and electricity. The other 5 stations are steam-only stations, meaning, as you might have guessed, they produce steam alone.
Steam generation can be summarized by this simple diagram. First, water is piped into the boiler. Con Edison gets its water from New York City's drinking water system. Once the water is in the boiler, fuel in the form of natural gas or oil is burnt. The burning of the fuel raises the temperature of the water to 1000 degrees Fahrenheit, thereby converting it to steam. On average, Con Edison converts 125 gallons of water into 1 million pounds of steam per hour. And once the steam has been converted, it is piped out of the boiler and into the steam distribution system. The steam distribution system is 105 miles of mains and service pipes that transport the steam to the customers. Mains are the larger pipes, usually 2 to 3 feet in diameter, that come directly out of the steam stations, whereas the service pipes are smaller pipes that branch out from the mains and connect directly to the customers.
The next system that we looked at, apart from steam, because it ties into the cogeneration or combined heat and power system or mechanism we looked at, is generating electricity. Essentially, you can generate electricity by rotating a coil of wires through a magnetic field, right? So this requires some mechanical energy input to do that rotation. The way this is obtained is by burning some fuel. You can burn natural gas, crude oil. Around the country, coal is widely used. Nuclear power plants also run off the same principle. So the heat that you obtain from burning these fuels, right, is used to pressurize and heat a gas, right? So you have this high energy gas now that you can shoot at a turbine. Once that happens, the turbine rotates, right, which translates this heat energy, which comes from the chemical energy of your fuel, right, into mechanical energy. And the mechanical energy is used to rotate, right, your coil of wires through a magnetic field, and you generate electricity in that way. The way that they do this with it's called a gas turbine, you'll never be able to use all of the heat, right, that you obtain from burning your fuel. There's always going to be some waste energy, which, you would like to avoid.
Here we have a schematic of a typical cogeneration system. To help you through it, we'll use something everyone's familiar with: food. To start, we burn our natural gas fuel source. This is equivalent to melting butter to jumpstart the breakfast process. The energy is used to power a gas turbine to generate electricity, for instance, 105 megawatts of electricity. This is analogous to using our melted butter to cook bacon, 105 megawatts of delicious bacon. We recover waste heat by using a heat recovery steam generator. Now we apply that heat by using it to boil water, which is put through a steam turbine, generating, in this example, 60 megawatts of electricity. This is akin to using our recovered fat to cook eggs, 60 megawatts of delicious eggs. At the end of all this, there is still more energy, or cooking fat, left for use. With cogeneration, this leftover heat is put into a steam system, while the grease can fulfill a variety of culinary needs. Overall, we have 165 megawatts of energy, from a single round of combustion.
The significance of this process is its efficiency. Each step along the way, starting with combusting our fuel for the first round of electricity generation, leaves a certain amount of waste heat. The beauty of cogeneration is that additional steps are added that harness that waste heat. Each step yields about 20% greater efficiency. Thus, while single-cycle generation is 40% efficient, tri-cycle generation yields 80% thermal efficiency.
Here we have the intensities for various fuels used in power plants. Highlighted are two of the main fuels used by Con Edison, namely number 5 and 6 oil and natural gas. One concern when looking at these values are comparable units. If we look at the pounds of carbon dioxide released per unit volume, we are given the impression that number 5 and 6 oil are much cleaner than natural gas. However, we cannot compare 1 gallon with 1,000 square feet. A more appropriate comparison would be the carbon dioxide emission per million BTU. Here we can see that natural gas releases less CO2 and is a cleaner fuel to use.
So, we're talking about carbon dioxide, but what exactly does this mean in terms of benefits? Well, carbon dioxide is a greenhouse gas, and as a result, the more carbon dioxide you have in the atmosphere, the more light and heat energy gets trapped inside the Earth, which makes the Earth warmer. The big repercussion of this is that you have a lot of polar and glacial ice caps melting, which causes a rise in sea level and a rise in ocean temperature. And these changes can cause drastic changes in ecosystems, and especially for humans, for example. A lot of societies depend on glacial water for drinking water, so if that is all gone, there will be a crisis. Two other major pollutants are nitrogen oxides and sulfur oxides, which are released through fuel combustion, particularly that of fossil fuels. The existence of these chemicals in the atmosphere can cause respiratory illnesses. They are also harmful because they mix with water in the atmosphere, making that water more acidic. This acid precipitation can have devastating effects on plant life and can permanently alter ecosystems. For example, eutrophication occurs when excess nitrogen, often from acid rain, is incorporated into aqueous ecosystems. This causes nitrogen-consuming organisms like algae to proliferate and deplete the levels of oxygen in the water, which is detrimental to other organisms in the ecosystem. Behind me is Con Edison's 59th Street steam plant. It was designed by Stanford White at the turn of the century, and it really epitomizes turn-of-the-century architecture. Since Con Edison converted it into a steam plant, there have been really detrimental features to the facade. They boarded up windows, cut service doors into the original facade, and replaced the 5 original smokestacks, which were designed to look like steamships, with one giant, ugly smokestack. Since Con Edison converted it into a steam plant, the building has remained largely empty. The ideal solution for preserving this landmark of 20th century architecture would be to remove the steam equipment and relocate elsewhere. This would require a replacement facility to generate the steam currently provided by 59th Street. We proposed building a cogeneration plant that could equal the steam output, which would preserve Stanford White's building and be inherently more efficient.
This chart quantifies the amount of fuel that would be saved amongst other benefits. Perhaps the most important of these is the positive environmental impact from pollution reduction. It would not be fair to compare cogeneration and the current operation, which is steam only. A comparable electrical output must be considered as well. These rows show the steam capacity, output, and pollution emissions for 59th Street. We chose to look into a 100 megawatt cogeneration facility, the capacity, outputs, and pollution data for which are highlighted here. Annually, this plant would produce slightly over 800,000 megawatt hours of power. In order to make our apples-to-apples comparison, we needed to consider an electric plant with 59th Street, as it produces only steam. We chose this plant because its output matches that of our 100 megawatt cogeneration plant. Though the two options have relatively similar carbon dioxide emissions, one can see that the cogeneration facility is much cleaner in terms of sulfur dioxide and nitrogen oxides. After considering the state of the building at 59th Street, the resources produced there compared to those possible with cogeneration, and the effects of each on the environment, we conclude that the replacement of Con Edison's 59th Street steam station with a 100 megawatt cogeneration plant would make a significant contribution to our city's ever-evolving sustainability.
The sun is a mass of incandescent gas, a gigantic nuclear furnace where hydrogen is built into helium at a temperature of millions of degrees. The sun